Hi, welcome back. In this videos, I will explain to you what is interrupts in the microcontrollers and how to use interrupts for multitasking in a PIC microcontrollers. Okay, before we do the programming step, I will explain to you what is interrupts and how does it works. So interrupts is a hardware inside a microcontrollers where it receives the signal or interrupt signals and can pause or can stop the CPU or the microcontrollers from execute the main programs. It just stop for a while and then it go to a special regions on the ROMs or to do some special commands. After finish the special commands, they call it the interrupt vectors. After finish some special task here, the CPU will go back to the main programs and restore or do continues the command from where it stop or pause before the interrupt signals. So that is the interrupt. That's why they call it the interrupts. In order to do the interrupts, there is a mechanism behind. It's based on the program counters. I have to remind you that inside the microcontrollers, we have the ROMs where you keep your programs. It is unchanged while you execute the programs. Where, for example, you have the main and some others command, the first command, the second command, and so on. But the ALU or the microcontrollers execute the commands on the ROMs based on the program counter. If the program counter keep the values of 000, then it will look at the ROMs at the register or at the bank zeros where what is the command you store in here and then it will execute. Then after finish this command, it will automatically increase the program counter to 1. Okay, so it go next command, and then after finish the next command, it will increase the program counter one more time. So it will basically execute one to another. So the interrupts is a hardware module. It will interrupts the ALUs. It makes the ALU change the program counter values back to the reset values. The reset value, they call it the interrupt vector, and in the PIC microcontrollers, that is 04. So whenever an interrupt appear to the microcontrollers, it will reset or it will assign the program counter to 04, and then the ALU will go to the address in the ROMs, that is the interrupt vectors, where you keep some commands here or some special task here. They call it the interrupts service routines. Okay, they call it the interrupt service routines. And then the ALU will execute. After it sees the return command, then it will go back to where it's left before the interrupts. This timeline will explain more about the mechanisms. So we have here the system clocks, all right, and then if a interrupts, for example, the external interrupts appears here, all right, then an interrupt will execute. That is, there will be some latency. There will be some latency or delay after the interrupts, that the program counter will reset to 04, and then it will execute the contains the ISR stored at the 04. In order to use the compilers, you have to understand what is the sources of the interrupts and how to use the C programming to make it works. So in the datasheet, you will see that interrupt may occur with the timer zeros, with the external interrupts, and with the others values of the interrupts, and so on. There is kind of any hardware inside the microcontrollers can generate an interrupts, ADCs or the uh, transmission or something, okay, where you have some bit in the RAMs can enable and disable the interrupts mechanisms. Alright, we can go to the instruction from the microchips compiler's user guide, and then we browse to the interrupt sections where you can read the instruction for the interrupts. For example, if I want to write the interrupt service routines, that is the function that call every interrupts appears. Then you can put the macros dash dash and interrupts specifiers to make it the interrupt functions. For example, like this, they have it. So we have the void and then dash dash interrupt that point that this function will be my interrupt routines. Okay, this will be called automatically every interrupt appear. Okay, and then you can check the flag, or you can check what is the interrupts occurs. But don't worry, we use the MCC to generate the code, so it will automatically create this function for you. For the compiler CCS Pixie, they have another macros that int and then interrupt specifiers that tell that this is my interrupts functions for the analog to digital conversion. And so on. You have so many others specifiers for the interrupt functions. Okay, that is the interrupts. Now I will demonstrate the use using the interrupts on the MCC. So we have here the blanks programs. We use the internal clock system. We generated 1 megahertz. Then I will see in my source my main programs. Okay, that's it. Alright, and the main code is supposed to be here. Alright, then I can make the timer zeros interrupt. Okay, then for example, I want to make it the oscillation, and then an enable, and then I take the 100 millisecond. Alright, and then I enable the timer's interrupts, where whenever the timers overflow, it will create an interrupt. So every 100 millisecond will appear one interrupts. Alright, then I can generate. There we go. In my MCC generated files, I will see my timer zeros, and the settings for the timers work at 100 milliseconds. Alright, the reload value. Then I also have my interrupts manager files. Alright, where every interrupts it will call these functions, and then the MCCs will execute these functions. Alright, this function. These functions will place at your timer zeros right here. You can write your own execution code here, but the MCC is advised to have our own the interrupt handlers or the interrupt service routines, that we can use this function to set the names of the interrupts. For example, I copy this and I go to the main, and then after the system initialize, I can specify my all functions. Otherwise, I don't want to use the names here, because if I use this, I have to rewrite or I have to modify the generated files. That's the microchips or the MCC don't like it. They advise us to modify everything inside the main programs. Okay, then I can write it, for example, my T0s interrupt service routing. Okay, this is the name of the functions, so I have to write it void my T0s. Okay, and then this is my functions. Alright, I will make the reverse opposite every time the interrupts appear. So I make this port C for output. Alright, and then I generate it again. Okay, and then I write my functions here for lat C bit dot lat C0 equal to the reverse of it, lat C bit dot lat C0. Okay, that is my function. And then you have to, of course, enable the interrupts. They have already write the function for us. Just uncomment this. Alright, let's check. The commands is just only the enables a bit in the interrupt control register. Very easy. Alright, then we double check, we generate it again, and then we build. Alright, in my main programs I do nothing. The interrupts will automatically generate every 100 milliseconds. Alright, it's because my setting for the timer 0 is 100 milliseconds. Okay, that's it. Let's check it. I have already the code here where I can view it by the virtual oscillations. Okay, let's check. Interrupts, this one, productions, okay, 1 megahertz, okay, and then run it. Alright, then I can see my interrupt service here. 1, 2, 3, 4, 5 units. Every unit take 20 milliseconds. That's it. That's 100. So 100 milliseconds. I change my RC zeros from 1 to 0 and from 0 to 1. And it automatically. So that's it. That's how we use the interrupts in the microcontroller, in the big microcontroller. Using the MCCs is very simple. So we put the interrupt enables, and then we set the interrupt handlers. We write the names, and then this is the code we want to execute every interrupt appears. Alright, this is your exercise. The first one, you can write your PWM or pulse width modulation. I call it the soft PWM with 8 timers. For example, here we already create 50% duty cycle of a PWM. You can modify it a little bit to make it the functions that you can set for the period and then the duty and also you can write it start or stop the functions. Okay, then the next exercise, you can read an encoders. An encoder is a device that attaches to the motors that will generate the pulse. Where you read the pulse, you can estimate. Remember that you just only can estimate the speed of the motors. Uh, there are some resources on the internet that explain how the encoders works. Basically, you have the dish, all right, and then you have the light emitting diode can detect this rotation by the track A and B. Then you can count or you can measure the times of the pulse here to estimate back the rotation and the speed of the motors. Okay, I will put a link for your reference. We will do the next exercise just very fast. So we have two ways to measure a speed of an encoder. The first way that you take the pulse countings that you have to generate a specific of times. So you take, for example, 200 milliseconds, and then you can count how many pulse that appear in that amount of times, and then you have the times and you have the length or the rotation. You can make the rotation divide by the times to make the speed of a motors, or you can count or you can measure one pulse period here. You take the interrupts and then another interrupts, then you count how many seconds, how many microseconds in the amount of one pulse. All right. For example, we take the pulse countings. For example, in this exercise, we take the encoder with 360 full pulse per revolutions. Okay, let's do some calculations here. We have 306 pulse per one revolution. Okay, one revolution, and then one pulse would take 1 over 306 revolutions. Okay, we take multiply here and then divide here. So we have n pulse. For example, we read the n pulse during the amount of times for 200 milliseconds or something would be n divided by 306 revolutions. That is the way of traveling. Okay, and then if we read it in 200 milliseconds for the timer interrupts, for example, that we read n pulse. Okay, we read n pulse, and then in 1 minute, because we want to count the revolution per 1 minute. 1 minute would be 60 seconds, and then 60,000 milliseconds. Okay, and then the amount of time would be the amount of pulse would be 60,000 multiplied by n and then divide by 200 milliseconds. Okay, and this is this amount of pulse. Okay, and this give us the speed that we take this one for the revolutions per minute. Okay, this would be 60,000 divided by 200. Okay, and then multiply with n the number of poles and divide by the 360. Okay, that's it. That's the RPM, the revolution per minute or round per minute. So that's it. That's the equations that we need. Let's take 60,000 divided by 200 and divide another time for 306. Okay, that's the value. Okay, all right, then I have to change the code for 200. Okay, generate, and then I need the external interrupts. All right, the rising edge, generated again, and then come to my files, the main files. This is my T0 interrupt service, and then I need to have another interrupts for the external interrupts. Okay, the external interrupts here, where I needed the external interrupts have the similars like these interrupt handlers. Okay, copy this, open the mains, and then modify it to my external interrupt service routine. Okay, where I want to put it here, void. Okay, and then void. Okay, so in my hardware, this is my encoders with the motors. I connected to the interrupts at RA2. Okay, where if you can see the grid managers here, it takes the external interrupts at the port A's RA2. Okay, it's locked to the function of the interrupts. Okay, I connect it here, and then I can count for the pulse. Every rising edge, place it here. I will count 1. Alright, so I declare my variable unsigned chart. Okay, and then pulse count. Okay, for A channels. Alright, A count. Then I just increase every time it meets the interrupts. In my timer zeros, I will calculate how many count every 200 milliseconds. So after calculation, I have to reset it to 0, so the next time it will count it again. And then A count will be my numbers, and then the motor RPM, or the speed of the motor, would be this value multiply with my values here. This is the number. Copy and paste it here. Okay, alright, this is the motor speed. Then I have to make a declare, so I want to make it the float motor RPMs. Okay, equal to 0 at the first time. Alright, that's it. That's my function to calculate the speed of the motors. Then I need somehow to display it. So I take the UART module and then transmit. Okay. Alright. Then I use my printf function that I have to include the stdio.h standio and I write my own put chart. Okay, chart. Okay, and then I copy my UART right. This is the read. Okay, this is the right, the chart. Okay, so that I can use my printf function. In my main programs, I only need to print the RPM, motor RPM, okay, equal to the float f, okay, and then I can write my motor RPMs here. Alright, that's it. But I don't need to print it so many times, so I take the delay for 500 milliseconds, for example. So every 500 milliseconds, it will print out the motor speed. Okay, and then the motor speed will calculate automatically every time the interrupts. Alright. Okay, before we do the simulation, I want to change the encoder's counters to long to make sure it not overflow my variables for the countings here. And then I change the update rate for 300 milliseconds. Okay, let's build it. Alright, let's check it again. Alright, that's it. So it takes 600 RPMs. Alright, this is my pulse created by the encoders, and this is my reading values calculated. So it a bit late update. Let's check it. Alright, there are some errors here because in my interrupts there will be some latency, and there will be some function call, for example. Then my reading timers will not exact the 200 milliseconds, and also the pulse counts may missing during the first start at the beginning and the end of the periods. It may miss some pulse here, so the value is may got it wrong. We need to do some calibrations here, so we take the reading values of 568. All right, we take the 568. Okay, but the real value would be 600. Okay, 600 divided by 8. Okay, then this is my calibration parameter. I take the multiply with 0.8333333. Okay, that is, this is my new parameters, 0.88. So I change this to my new values here, 988. Okay, that's it. And then let's check again for the simulations and building success. Okay, and then run. Okay, 600 and then 600 this time, so which we need to calibrate a little bit. So alright, let's change it to 300 RPM. Okay, this is the reading values. This is okay. Then let's change it to another values to make sure the calibrations. Is 400. Okay, this is 400 reading values. Okay, then it would be okay for 200. Alright, So this is my calibration and my readings for the encoders. We can do the second way for the pulse countings, pulse timings here. Alright, where we created timers, and then we trigger the timers every pulse interrupts. So that's it. That's my videos for the interrupts and how to use the interrupt in encoder readings. That is the multitasking for the microcontrollers. I hope you enjoyed it, and see you in next videos.